So essentially, I've posted a revision of the Module 4 study guide. If you have previous copies or versions of the Module 4 study guide, make sure that you discard those. In the update, I went ahead and revised this section. Last Wednesday, before we broke for Easter, I had some additional information, and what I've done is consolidated some of this. I made verbal mention of domain name service, how when DNS servers are working between each other, they use TCP port 53. And when they're working with clients who are connected to the network that want to browse the internet, they use UDP. We're going to explore today in more detail what that really means. But it's really important to understand that that this information has been revised. I also went ahead and kind of reformatted this so that we could talk about ports that are a matter of concern instead of using the idea of scary, right? Whenever you see that ports 139, 445, 6, those are additional network exposures that are very common, but very problematic because there's a lot of needless exposure on a network when you have clients. You can use GRC shields up, and if you see a blue square and you hold your pointer over it and it lights up 139 or 445, there are simple changes you can make, and we're going to cover that in the last module. Ports 666, if you're into biblical or scriptural things, 666 is a reference to the devil. So if you see that port is open, or that's usually an active malicious exploit, that's usually very bad. 444 is also the same thing. If you see 3389, it means that part of your internal domain is exposed to the outside. So whenever you see this kind of thing with activity with some of the diagnostics like netstat or netsh, or you see it with GRC shields up, it's time to just take a moment and make some changes, because you don't want uninvited guests or data in your network. Does that make sense to everybody?
Yeah.
Okay.
Yeah.
So one of the things that we wanted to highlight before we got into a deeper review, I can go on with the study guide, and what the study guide is doing is pulling specifics out for the things in the material. And I've also updated a few more references here. There'll be a third additional just short slides. The flip side of DNS, this is really important. There's only a few slides, but it's very important information, and we'll show you that in just a second. There's going to be another one that talks about the most common types of network applications based on layer 4. And so there'll be another short one here. This is the one you want to spend a little bit of time on, and where we're going to spend the lion's share of our time here. There's a lot of rich and additional content to supplement what's in the study guide and the addendum. And that's going to be important. We're going to kind of cherry pick or highlight some key slides. And it's a very long reference, but again, we want to share the pit stops, the most important pieces of that. So when we're talking about application types, right? This there are many layer 4 or transport layer protocols that are part of the TCP/IP protocol suite. And so you hear about IP networking, and oftentimes you hear the term TCP/IP. And that's because TCP is very prevalent when you have server-based resources online or in a local network even, right? And there is a session that's formed that is based on a connection, right? And there's a special handshake that occurs. And that special handshake ensures that the connection between the server and the client is stable. And it also serves to guarantee delivery of the packets, right? So UDP is a great way to get quick information and especially streaming information to and from resources and clients. And essentially, TCP and UDP, when you see online resources being offered to connected clients, very much of the time, a vast majority of the time, it's either TCP or UDP. So we did talk about clients, right? But a lot of sockets, and remember a socket is what? There are two components in a socket. Does anybody remember what forms a socket? Anyone?
Like what are the parts of the socket?
Yes. What are the parts of the socket? So you have a server that's offering resources. You have a client that wants to connect to the resources and they want to start a session. And the way the session is started, there is a server that's listening after it opens a socket, a network socket. And then there are clients that attempt to join the session once the client has a socket. How do you identify a client or a server on the network? What's the most common numerical reference we have to work with?
IP?
IP network. IP network address is correct. Thank you. And it's if you put a colon after that network address, there's another number that follows. Does anybody remember what the smaller number is?
The port number?
Yes, excellent. Thank you. So both the client and the server form sockets based on the IP network address, and depending on the app or application, the network application, if it's a familiar or famous or registered application, there is a designated port number that the server works with. TCP protocols guarantee delivery. And basically, you're dealing with data packets or files. UDP does not. So there's quick information or bulk information or streaming content. We often say that there are messages like email messages. We want to guarantee that an email message in its entirety gets there, even if the packets are going different routes, even if the packets are traveling through different portions of the network. When it gets to the other end, when the email server is delivering an email message. So this is message based. Think of a message as a file and it's chunked up into different packets, right? Those packets have to be reassembled in the order and we have to make sure that everything's there. So remember the thing about the packing slip and CRC? Does everybody remember this? Packing slip, yeah, CRC. So TCP establishes, for the session, it establishes a connection. UDP is often referred to as a connectionless session, but there's still exchanges of information, right? So it's the three-way handshake, right? And there is a slide that you can look at, slide 503, and it talks about the three-way connection. And that's it for this particular set of slides, right? That's all we're worried about here. Any questions? Now, I also wanted to touch on DNS. We're going to circle back to DNS many, many times. And what I'd like to do now is introduce different aspects of DNS along the way. So there's another reference that's posted in the module now. It's called the flip sides of DNS, right? Essentially, DNS has it performs two really different but very important roles. And whenever you see about DNS advertising a resource, that means that it's part of the authoritative, it's providing authoritative answers for that network resource to other clients that are trying to find or resolve the network address. When clients are trying to find a network address, when they're trying to locate a resource, they're performing something called recursion. They recursively ask each of the DNS servers, where do I find myjam.net? Myjam.net. I have a friend that created an innovative domain name, and they've started, this is for music exchange, myjam.net, right? I'm just using this as an example. So you have connected clients that get on the internet and they want to resolve or look up where is myjam.net, and they're going to go to the DNS servers, right? Now, the DNS servers that help resolve that answer know where to find the DNS server that has those records, that is authoritative for that role, right? So we have other DNS servers that perform an extra role. They store the records for myjam.net, as an example. And that means that they are authoritative. They can tell other clients, and more importantly, other DNS servers, hey, this is where you find myjam.net. And it's first the .net servers that say, hey, of all the .net servers, here's where you find myjam servers. Here's where the zone for myjam is in the .net primary, in the first level or top level domain we would call .net, right? So when you think about a DNS name like Amazon.com, there are many .coms, but there's a DNS server, there's an authoritative DNS server for all of the .com domains in the world. And then there's an authoritative DNS server for Amazon.com. But it's authoritative only for Amazon. It's not authoritative for .com. So when people are trying to find things on the internet, first they start with the top level. They start with the .gov or the .edu or the .com or the .net or the .org. Those are called top level domains. And those domain servers say, hey, of all of those .nets or .orgs, I know where to find myjam. I hope that makes sense. We'll talk again. We're going to come at this from many different sides, and we're going to explain this in many different ways. And we're going to do this over time, over and over again, because we want people to fully understand what's going on here. There's two animals in every DNS server, the one that helps you find things on the internet and the one that tells everyone else, hey, I'm in charge of that. I'm in charge of .myjam. I'm in charge of myjam.com. So in the packet tracer environment, it allows you to set up configuration criteria in a GUI, right? And it allows you to use useful labels in your process. And there are a lot of different sockets that are formed, either TCP or UDP. And we're going to come back to this, but TCP guarantees delivery, UDP does not. If it comes to quick, bulk, or streaming content, that's typically a connectionless session. Reliable two-way connections deliver, they guarantee delivery, right? And here's the part that I want you to notice. On this final slide, there's an extra link, okay? And this is really important. I want you to click this link. There's a YouTube that you want to watch that talks about resolution and authoritative roles, right? So this is going to be a helpful thing to watch. And then as you're getting ready for our assessment, I'm going to take a little bit of time to talk about special issues for DNS, like how to keep it secure and how DNS errors are resolved. Because if it has to do with a name on a network and something doesn't work, it's probably DNS. And if you have some quick tools, you can make life easy. Then we're going to take your DNS domain. You created a domain name. Your first assignment was to create a domain name. Just remember to go to the link. Go to the link. Any questions about what we just shared here? Okay, so I want to come back to this. Can everybody still see my screen? Are we still good?
Yep.
Okay. So if we come into here, some of you have not submitted your own custom domain name. And you need to do that because by next Monday, this time next Monday, 11 a.m., you will have to have completed a creation of your own domain. So here you're inventing the name, so to speak. You've come up with your own name. And I'm going to use myjam.net as an example. So I've just conjured up myjam.net. And your solution is to pull up a screen with me. You're going to have appointments. There are specific times and days where you're going to schedule a screen share, and I'm going to pull you up onto the domain name server, and we're going to create your very own zone. Now, a zone is the set of records. The zone is the set of records that tells the rest of the world, here's where you find myjam.com. So you have two different kinds of zones on a server. There's one that's read-write. You can make changes. It's the master copy. It can be corrected or changed. It's called the primary zone. And then there are multiple copies on other servers. When a server contains a copy, even if it's only a read-only or reference copy, you can't make changes to it, but it's a copy of the zone. That's called a secondary DNS server. A secondary DNS server can tell the world, hey, this is where I find myjam.com or myjam.net or myjam.org, however you decide to create your domain name. The thing that I want you to understand, though, is that whether it's primary or it's secondary, whether it's a copy of the zone that can be changed and edited in the primary zone, right? Or if it's a read-only, I can't change this, but here's the information. Whether it's primary or secondary, both of those types of servers are called authoritative for the zone. So what we're going to do is open up the DNS server, create your custom domain name you submitted for 4.1. And then we're going to run the service. We're going to change a setting on your machine, and you're going to be able to browse to your website. We're going to create a splash page for something that could be your web server. And it's going to work from where you're sitting, from wherever you're connected on the internet. But in order to do that, we have to have a submission here. And there are still a number of students that haven't submitted their choice of a domain name, right? So I've taken the deadline off of this, and if you haven't submitted yet, you need to click into this and turn it in. Any questions about the expectation this week? Between now and 11 a.m. Monday, every one of you needs to spend 10 minutes on the screen with me finding out how the rest of the world does this on the internet. And it's really cool. The first time you see your domain name and other people are able to browse to it, that's pretty special. You're like, wow. So I could set up my own Google, my own Amazon, my own Apple.com. Yeah, you could. It's that easy. We're going to show you, and you'll log 5 points for doing it. And what I'm going to do is coach you and walk you through the changes on screen. So we're going to have a script to follow, and you're going to direct the traffic, and I'm your eyes and your ears on that machine. Okay. Now for extra credit, you can create your own DNS server and then set it up on your own DNS server. And that's a topic we're going to cover for another day. Any questions before we take up our next interest? So everybody knows that if you haven't turned in your domain name for 4.1, you got to get on it right now. Yeah?
Yeah.
Okay, that's the important thing. Okay. So I'm going to blitz the slides. There are 244 slides in this last reference. So this one reference inside here that says Internetworking Concepts Comer, I've kind of plucked the layer 4, layer 3, layer 7, or layer 5, if you will, details that are important in this module out of here. So there is a slide series for students that includes all the slides for all the chapters in the entire book. But this one focuses on the topics that we're gonna leverage for the rest of the time we have together in the course. Put another way, this is the one slide series you want to spend the next 2 weeks reviewing, and in particular, special slides. So I'm going to go ahead without further ado. Some of this is going to be review because you're going to go, oh yeah, I remember that. But then there's going to be other stuff that's going to appear to be familiar, sort of, because we talked about some of the aspects of it, like multicasting, right? So the vast majority of content out there is web-based. When we say social networking and blogs, that's still web-based. If it's in a web format and can be viewed in a web browser, even if there's an app for it, it's still a web resource. 90% of all network exposures and exploits occur through web or email or messaging. So whether it's email or texting or instant messenger, messaging apps, and web-based online resources, 90% of the resources we're dealing with out in the real world are one of those two, right? And network professionals see this as infrastructure, right? So they're thinking about the equipment and the software. This is just a quick statistical view of the growth of the internet and the number of computers. We believe by the year 2025, there will be about 30 billion, 25 to 30 billion. Hello. Not, see, this is 1 billion. This is in millions, right? So we had 1 billion devices on the internet around 2012, 2016. So on a logarithmic scale, right? It's very, very aggressive. So since the year 2000, there have been a much larger number of internet devices. We call them smart devices, smart appliances, intelligent things that you can connect to your Wi-Fi. And this is one of the reasons for the explosion. We refer to those generically as the Internet of Things. So the things in your house, when they become smart things, they're part of the Internet of Things. We have touched on NAT, right? So we're going to blitz through that pretty quick. One of the things to remember about networks is that there are explicit names for different types of networks. We've talked about the local area network, but there's another wrinkle or another acronym called WAN, and that means wide area network. That's a network of networks. So if you have 2 LANs connected, now you have a WAN. If you have multiple LANs in close proximity because there's a campus with many buildings, we would call that a metropolitan area network. That's like many local area networks, but concentrated in a single spot. WANs can cover intercontinental distances. Does anyone know what a PAN is? P-A-N? Anyone heard of Bluetooth?
Yes.
Anyone use Bluetooth for like headsets, headphones, printers?
Yes.
That's called a personal area network, and that's within 30 feet, right? So when you talk about biggest to smallest, this is the smallest, most personal. This is the largest that can span continents. And this is, oh my gosh, a lot of local networks all clustered together in a city or a campus, right? So when you're looking at the design of the internet, there are some profound concepts that have led to the development of these TCP and UDP protocols and how the apps work. And this is the background information, right? So one of the things that we have to do with the internet is work on an open standard basis because there are so many different brands, different models, different types of communications. And that's part of what we're dealing with. More than anything, it's important to understand that by the time you get to the internet or a network of networks, you have to have routers and you have to have routing. And that's where layer 3 comes in. You cannot have any functional routing between networks without layer 3 and without an IP network. But you can work with MAC addresses on a very large local network, right? So anything that's connected is generically referred to as a host. So a host can be a server, a host can be a client, and a host can be a hardened host in terms of security, in which case it's referred to as a bastion host. The word bastion means like castle or fortress, right? And we'll get into more of that in the last module, right? But basically, yeah, again, a lot of this is just quick review. You'll notice that we're working with version 4 of the IP protocol. Versions 1 through 3 were skipped, then version 5 was skipped, right? So the newest version is 6. And so I'm going to move pretty fast here, right? So you have applications that end up putting packets on the network, and then those packets are delivered out to the networks. And then on the other side, you have the flip of this hourglass. On the other side of the receiving end, you have networks that are delivered to a specific IP address based on the header. And then those packets are unpackaged, the payloads are released, and then the datagrams are taken up by the applications on the other side, which is, it could be an email client, it could be a web browser, whatever. The thing to remember is that the IP addressing is in the middle, and it's the basis for which everything works. If you have a switch, a network equipment device that has layer 3 capabilities, what that means is that it can accommodate multiple LANs and it can route between them. You can create routes on that switch. So it's kind of a hybrid between a router and a switch. The important thing to remember about IPv6 is that unless it's full scale and it's correctly implemented properly, you don't worry about it. They're going to say a lot of things in this slide series about IPv6, but I don't want you to worry about it. We just said that you can have a network that's pretty big with MAC addresses on layer 2. But could you have an internet that way? No, because you have different types of devices working different types of networking protocols. You can have Bluetooth devices, you can have Zigbee, you can have near field communication, you can have Wi-Fi, you can have all kinds of different protocols that utilize the MAC address. So MAC addresses are too general, and they're too, the MAC table would have to be way too large, right? The rest of this, we have, dotted decimal equivalents. They're called octets. We use CIDR. This is all pretty much stuff you've seen in other, we know how the address, the subnet mask works, right? So this is just to keep things fresh so that you can this is a good prep going into exam week in just a couple weeks, this whole slide series, right? So there are special IPv4 addresses like the 127, that's for loopback, and 240 and above are multicast, right? So let's see, let's find something here. So yeah, this shows different kinds of media. You have Wi-Fi, and then you have cabled, and you have a router in between. So a lot of this is intuitive when you flip through this. What I want to do is stop when it comes to things like this page where we talked about Anycast. Any computer can duplicate and repeat. So your network is sort of like a hybrid peer-to-peer network. Multicast is when you have a single source going to all sorts of different addresses. Again, we've talked about that. I'm not going to spend a lot of time on the IPv6 things. And yeah, it says why you would want to adopt IPv6. Well, it's nice to know this, but per square meter of the Earth's surface, you have 10 to the 24th addresses. I mean, that's crazy, but you'll never run out of addresses. So it's good summary information about this. I want to focus on the UDP and TCP portions of this. So I'm going to go ahead and click faster through more of this, and I don't want to freak anybody out. So does everybody know? I want you to, so this is the header or the address portion, right? So does everybody see this part right here in the center of the screen where it says source IP? You can see my pointer, right? Can everybody see my pointer?
Yeah.
Yep.
It says source IP address. That's the person, that's the host that's sending. Destination IP address. That's where the packet's going, right? So this is the header information for IP network packets. And so you have to have that source and final destination, right? And with IPv6, the header is formatted differently. It's organized differently. I just want you to be aware of that. So there are cases where you have routing involved and it talks about a next header field. We're not going to spend a lot of time on that. One thing I want to get to, though, we did talk about next hop in our previous solution. So when you have packets and they're forwarded, this is where the router is doing its job. A forwarding table is basically a collection of routes. Okay. There are no MAC addresses. It only uses IP network addresses. And so this is just another example of how those forwarding works. This is what you've already done. But let's get further up the stream and get to, oh, I love this diagram. So this is a good diagram that shows, okay, here's the frame header on layer 2 and the frame payload, and then this whole packet fits down inside the frame payload. And then when you get to layer 3, this whole payload is opened up to reveal a datagram with some other headers, right? That's how your datagram remains intact from end to end. That's how you can work these things. So the term MTU, maximum transfer unit, is the largest number of, it's the biggest chunk of data that you can send across equipment. Sometimes that's a constraint. So getting networks to talk to each other, sometimes this is an area where things don't do very well and they have to change the size of the transfer units. That's good for troubleshooting purposes. There are times because of that MTU limitation that they take a packet and they have to break it down into smaller packets, but then they reassemble it on the other side. And I just wanted you to be aware of what happens with packet fragmentation. Not going to get into IPv6 fragmentation. So address resolution, this is when we talk a little bit about resolving MAC addresses to IP addresses. That has to do with ARP. This is again kind of a review, but I want to get to the place where, all right, so when we talk about ARP message format, you have sender and receiver again, target, right? Sender and target, same kind of idea. The important thing to understand is that MAC addresses stop being used right here at the edge of layer 2, and from layer 3 on up, this is where you're going, right? You have to use IP addresses from the 3rd layer through the 5th layer if you work in industry, or 3rd layer through 7th layer if you work in computer science or research. So ARP is sometimes thought of as a security weakness. I'm going to go into that in more detail in the last module. Error reporting, you have contention, right? So we talked about the tools that you use. ICMP is called ping. We've used ping already, haven't we? Hello? Are you still with me? Can somebody
Yeah.
Yeah.
Okay. We used ping when we were setting up the routed network, yeah?
Oh yeah, yeah, for the module.
Yeah, the formal name for that ping protocol, it's part of the IP protocol suite, but it's not part of TCP. It's used for troubleshooting, so you can find out what's going on with your network with the hops. That's the main point for ICMP. And that stands for Internet Control Message Protocol, that helps you understand where where the stuff is going, right? So ping is one of those things. Path, ping, trace, route, those are all ICMP kinds of things. Those would be one of the primary exceptions to the statement I made at the beginning of class. What percentage of network traffic is either TCP or UDP? At the beginning of the class, I said such and such percent of all the network traffic that's going on, it's either this or that. Anybody remember?
90%?
90%, right? Better than 90, actually better than 90%. And so if you're troubleshooting and you need other tools, you're not using TCP, you're not using UDP, you're using ICMP, right? So there's additional information in here that's nice to know about how to manually configure your stuff, or how to get around challenges. There's additional information about DHCP and what it does and how it works to assign messages automatically. But that's not, and NAT, right? So it talks about NAT and why we do NAT and how that works. Now the transport layer protocols. This is where things get interesting. So it's around slide 123. Slide 123 is what we want to focus on. And I'm gonna blitz for like 2 minutes here so we can get to that portion of this, and then we're done for the day. So a network session helps two hosts with end-to-end communication, right? And basically, when they talk about endpoints, they're talking about hosts, and usually when they talk about endpoints, they're talking about clients, connected hosts that are receiving resources from other machines. This is the industry standard protocol suite. You notice they don't have layers 6 and 7. They leave 5 and 6 out, so they go right from transport to application. And that's significant, but we'll get into the other OSI model a whole lot more. It's useful to know this because there's a lot of troubleshooting and network management that occurs with this model as opposed to the OSI model. And there's more network application development when you create network apps where you use the OSI model. So the problems with transporting are, how do you make sure that everything gets there and it arrives in the right order? That's where TCP solves the problem, right? So when you look at how TCP works, this idea of a sequence number for each packet is important. You can't put things back in order if you don't have sequence numbers, especially if you have to fragment packets. So there's a good part of the TCP protocol that has to do with sequence, but even UDP information. Yeah, here's the IP you need for this domain name. That's UDP. That's what you'd send to a client that wants to find something on the internet. Even that has a sequence, right? So basically, UDP we'll go ahead and start our deep dive on UDP and then pivot and talk about TCP on Wednesday. This is where we'll stop today. Based on the material we've presented today, can anyone think of any interesting questions or comments or curiosities before we stop? Okay. Well, thanks for joining us today. If you haven't submitted a domain name yet, make sure you do. And then we'll be ready to start. I'll put out a schedule and you'll need to sign up for a specific day and time to create your domain name out on the internet, right? Stay tuned. We'll catch you on Wednesday.